Testing, testing, no testing. I'm not actually testing anything. Um, okay, we're moving on to chapter 2, but I'll just like maybe I'll spend a minute just looking at this. Um, Draw different color green. We have dot product, cross product. All of these is identities, BAC rule. Um, yeah, vector differential operators. Yeah, we know how to do this. We know how to do it. Well, we know how to do like I would say like everything. Yeah, yeah. And if we forget, we'll just come back here anyways. So spherical. I did a bit of cylindrical, like off camera, off stream. Ooh, Jacobian's integral theorem. Okay. Uh, Normally I don't really erase stuff, but I don't like how this looks. Um, Good enough, I guess. Good enough. Draw. We will stay on green. Is anyone here? No one is here. Okay. Ah, shoot. Transformations and the laws of physics. Physics deals with physical events in spacetime. Given a physical system at a given point in spacetime, we would like to know how it looked in the past, how it will evolve in the future. In addition, we wonder if it might be related to other relevant events in the past, future, and at other points and orientations in space. We wonder if it might be related to other events in the past, future, other points and orientations in space. To answer these questions, we need space-time machines to move us back and forward in space-time so we can examine the situation ourselves. These space-time machines are called space-time transformation operators. Um, if I'm too close to the mic, maybe I should type that in chat. I don't know if people coming in will see chat, like my message in chat. Tell me if mic is too close or something. If anyone uh, joins. Okay. Um, these spacetime machines are called spacetime transformation operators. Operators keyword. In this chapter, we show that the transformation operators in spacetime can appear as square matrices, and can appear as square matrices and as differential operators. Square matrices can be multiplied into column vectors, square matrices, column vectors, to give other column vectors. Functions can be differentiated to yield other functions. We show that in space time can appear. If we represent the state of a physical system by a column vector or by a function of position and or time, its evolution in spacetime can then be symbolized mathematically as a consequence of an operation. Its evolution in spacetime can then be symbolized mathematically as a consequence of an operation by a square matrix or by a differential operator. Column vector or function. Transformation operators also appear in statements of physical laws. A law of physics codifies the behavior of a class of physical events. This new headphones I have on uh, it's making everything like really quiet. Like normally I'm used to hearing the background noise of my room and outside, but I can hear like nothing. So yeah, it's kind of weird. Um, Transformation operators also appear in statements of physical laws. A law of physics codifies the behavior of a class of physical events. Law of physics, bling, the behavior of a class of physical events. Since the evolution of physical events can be symbolized by transformation operators, a physical law is essentially a statement concerning one or more of these operators. For example, Newton's equation of motion in its simplest form, this describes how the position of a mass is changed or transformed in response to a driving force. This describes how the position of a mass, so you have the mass here, this is the position here, um, is changed or transformed in response to a driving force. So the position is changing because of this thing, um, depending on the values inside here, it changes the position. Uh, an even simpler physical law is contained in the 1D wave equation. This states that the wave motion will appear if the transformation operator del x del 2 del x squared in space induces a change with the same. This states that the wave motion will appear if the transformation operator bling in space induces a change with the same sign as and proportional to that caused by the oh my god. This states that the wave motion will appear if the transformation operator, I'm looking at the equation. So this minus this equals 0. This equal this, like if you carry it across. Well, this combination here because it's a bracket. Okay. Wave motion will appear if the transformation operator in space induces a change with the same sign as and proportional to that caused by the transformation operator during in time. We thus see that a wave is a manifestation of a certain correlation between disturbances in space and those in time. A wave is a manifestation of a wow, blah blah blah. Nonsense. We thus see that a wave is a manifestation of a certain correlation between disturbances in space and time. So del x, right? There's a change in x. So we're calling that a disturbance. When x is changed, it is a disturbance. So del 2 del x squared of u xt equal 1 over gamma squared is y, gamma, v. Oh yeah, speed of light, I assume. I don't know. 1 over v squared del 2 del t squared u u xt. is a manifestation of a certain correlation between disturbances in space and those in time. Besides simple spacetime properties, a physical system may also have additional internal attributes that may or may not be describable directly in the spacetime language. Also have additional that may. So you can't tell everything based on the equation. There's more attributes in there. Their transformations are often represented in matrix form. Besides simple spacetime properties, a physical system may also have additional internal attributes. So I guess you can see the internal attributes from matrices. That's what they're saying, yeah? Directly in the spacetime language. The transformations are often represented. Since successive transformations add up to a total transformation, matrices, like spacetime transformations, form mathematical structures called groups. Modern physics is often a detective story in which an unknown group structure behind relevant experimental observation is to be identified. In this way, new physical laws can be established even before we can describe what's actually going on in space-time terms. To help the reader in group theory, this chapter closes with a short section describing a number of common matrix groups. Okay. I roughly understand. I should drink some water. Rotations in space. Matrices. Besides scalars and vectors, which are linear arrays of numbers, we also have rectangular arrays of numbers called matrices. Matrices are particularly useful in describing rotations in space. By a rotation in space, we mean either the rotation of a fixed point in space about the origin of the coordinate system, the the coordinate axes being fixed, or the rotation of the coordinate axes about the origin, the point in space being fixed. It is obvious that these two rotations are simply related to each other, and in the present context it is more convenient to consider the second type, the rotation of the coordinate axes. Okay. Space, either bling or bling. Okay. Let us therefore suppose that we are interested in the position r of a fixed point in space in two coordinate systems related by a rotation. So r doesn't move, but we're just switching between coordinate systems, but the only difference between the coordinate systems is one is rotated slightly. Maybe not slightly. We ask what withdrawal rotation fixed. We ask what is the relation between the new coordinates and the old coordinates x1, x2, x3. The answer can be obtained readily by writing the old unit vectors ei in terms of the new vectors e1, e prime 1, with the help of the completeness relation, a really equation. ej equal There's a really old equation. Ej equal to dot product of dot product dot product. So you're basically dot products are kind of like projections, right? You're projecting one vector onto the other. So over here you're projecting e prime 1 into ej, e prime 2 into ej, e prime 3 into ej, and then adding them up to be like, oh, all of you. Hmm. What is the relation between the new coordinates and the old coordinates? Okay. Ej equal the sum of ei prime, this guy, where this guy is, oh my god, ei prime dot ej. Well, yeah, this is just another way to say these things. Ei prime dot ej, ei new dot ej old equal cos theta ij. The dot product is ab cos theta, but since we're dealing with unit vectors, the magnitude is 1, so it's just cos theta ij. A and b equal 1. Ei new dot ej old new old. What is the relation between the new coordinates and the old coordinates? So ei is the what is equal this? Ej, like this big equation here, is a direction cosine. Thus r equal x. Okay, r, that's the point. That's just a point in space. R equal x1. Then you have this thing here, which is the ej. Yeah, e1, e1 blank, e2 blank, e3 blank. Position vector equals x1 this, x2 this, x3 this. That is xi prime, xi prime, xi prime, where's that is xi prime equal blank x1 plus blank x2 blank x3 equal this. Summation the difference between this guy and this guy, ij, xj, x1, 0, 1, 2, 3. Okay, let me change this guy. That is xi prime equal this, with the indices j for the old coordinate system appearing together side by side in lambda and x. The summations of equation 2.2 and 2.4 are the same as those for matrix multiplications, as we shall see shortly. For this reason, equation 2.4 can be written conveniently in the compact matrix form. x1 prime, x2 prime, x3 prime equal lambda 1, 1, blah blah blah, x1, x2, x3. Or x prime equal lambda x, where x and x prime are the column matrices, also called column vectors. The 3x3 matrix, lambda, let's just call them the names, lambda, x, x well, x prime, and x. The 3 by 3 matrix lambda is a tabular array containing the 9 direction cosines between the two sets of coordinate axes. It is called a transformation matrix, or more specifically, a rotation matrix. Transformation, well, I can just underline it, right? The xy or okay. The xy or 1, 2 axes are rotated by an angle theta in a positive counterclockwise direction. As shown in figure 2.1, what is the resulting rotation matrix for the transformation? What is the resulting rotation matrix? Resulting rotation matrix for the transformation of the coordinates of a fixed point in space. We note that lambda 1 1 equal e1 prime dot e1. Okay. I'm just gonna stare at this. Is there anything else coming up? I think I'll just stare at this for like 5 minutes to see if I digest anything. Let me clean this up. Okay. What is the relation by... It's obvious that these two rotations are simply related to each other. In the present context, it's more convenient to yeah. Let us suppose that we are interested in the position R of a fixed point in space in two coordinate systems related by a rotation. Let me just put R here. R is this in the first coordinate system, R is this in the second coordinate system. x1, e1, x2, e2, x3, e3. So, I might as well try it, right? Okay. R equal x1, e1. Let's say x1, x2, and let's say x3 equals 0, right? Now we rotate this guy. Cyan. Is this even cyan? We rotate in the coordinate axis. It is over here now. It's over here now. From here to here. Now we have x1 prime in this direction. We rotated it from there to there. Okay. x1, x2, x3. What is the relationship between the new coordinates and the old coordinates? New coordinates, old coordinates. The answer can be obtained readily by writing the old unit vectors in terms of the new vectors. EI, with the help of the completeness relation. EJ, EI, E1, EJ equal E1 prime, E1 between the new coordinates and the old coordinates. The new coordinates have the prime on it. So these is the new guys, right? This is the old guy. This is the old guy. The old guy equal the new guy projected on the old guy. New guy projected on the old guy. New guy projecting the old guy, new guy projected on the old guy, multiplied by the vector. Okay. This is E1 prime. This is EJ. Over here is EI E1 prime dot EJ. E1 prime. Why are we multiplying by E1 prime again? EI on EJ. Boom. EI and EJ. Come down here. So we have this magnitude, and now it's pointing back in this direction because you multiplied by E1 prime again. Plus E2 prime. I guess the point is to be like, this is how much, like what percentage, how much E1 prime is in the EJ direction. So it's kind of like a fraction. Like how, like if you were like an alien, or like you were also kind of human, like interspecies, I don't know. You'll be like, oh, I'll find a dot product to be like, how much human are you? How much are we alike, my friend? So that's just what this is, and EJ equal this amount of E1 prime, this amount of E2 prime, this amount of E3 prime, this amount of E2. And they should all add up to 1, maybe. Should it? Should they all add up to 1? Should they all add up to 1? That's another question. Okay, you have a direction. Now you have this guy, theta, theta. 60 degrees, 30 degrees, and 45 degrees? I don't know. Is that even possible? Easy. Okay, let's just not even think about this guy. Not even think about easy. EI dot EJ. Cos theta IJ. Cos 30, cos 60. Does that equal 1? I forget. Does it? Cos 0 and cos 90 is 1 plus 0. I feel like this should be equal to 1. I feel like that's the case, right? Okay. Hopefully that works out for 3 angles as well. It's kind of weird. Okay, now let me actually look at these indices here. So lambda ij is what? Lambda ij is old guy, new guy dot old guy. EI prime dot EJ. EII. EJ equal summation of EI prime, this guy IJ. Where it goes from 1 to 3, right? So that if this is 1, then 1J, 2J, 3J, 1J, 2J, 3J. EJ equal E1J, E1J, E2, 2J, EJ, E3, 3J. Yeah. Maybe I don't even need to look at this. Like it'll come to me eventually. Okay. X1. X1, that's like our original length. Our original length. Does R equal X1 EJ? Okay, I see. R equal X1 E1 plus X2 E2 plus X3 E3, right? We found that E1 is this big thing, so we just put it back here. Okay, I get it. And EJ is just made up of these guys. Xi prime equal xi prime equal this plus this plus this. EJ equal the summations of EI prime lambda ij. Xi prime. What is Xi prime? X prime is like the new length, right? So Xi prime. This is just one length there. One length. One length equal small length plus small length plus small length. Right? Yeah. To find for one new length, we need to take into consideration how each length um how each length so lambda is just cos theta, right? Is all of this has to do with projections, is my theory, right? So to find for one length, you find the projection of each of the other lengths towards this length. I get it in my head. That is xi prime equal cos theta ij, cos theta ij, I1, okay. With the indices of j for the old coordinate system appearing together side by side in lambda and x. The summations of this and this are the same as those for matrix multiplications, as we shall see shortly. For this reason, it can be written as this: x1 prime equal I1 boom, 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 boom. Okay. Where x and x prime are the column matrices, the two vector matrices, blah 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 blah. 9 direction cosines between the two sets of coordinate axes. Two sets of coordinate axes. Cos theta ij. Cos theta ij. Okay. X. No, let's not use X. E1, E2, E3, E1 prime, E2 prime, E3 prime. There's an angle between these guys, angle between these guys, angle between these guys. Angle, 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 angle. So 9 direction cosines. Cosines 9 lambda ij's. Okay. And even though lambda I, you might think, oh, there's no angle here. It's I and I. It's the same guy. It's not the same guy. It's not the same guy. It's a EI and an EI prime. Not the same guy. Okay, now we can move on with our lives. Damn, back at it again. Yeah, I've been doing it for a week. And I do this late at night, which is like 2 a.m. and stuff. And I do it at 2 a.m. because I know I'm not really doing anything else. So I can be more consistent since it's at night. But that's just me. The XY or 1-2 axes are rotated. Example 2.2.1. The XY or 1-2 axes are rotated by an angle theta in a positive direction, as shown here. What is the resulting rotation matrix for the transformation of the coordinates of a fixed point in space? Okay, so let me try and do this. Lambda 1, 1, lambda 1, 1, lambda 1, 2, lambda 2, 1, lambda 2, 2. What does this mean? Let me call this the old coordinate system. This is the new one. So E lambda 1, 1, what does that mean? That means lambda 1, 1. That is the angle between the new one and the old one. This is the old one. This is the new one. So it's theta, cos theta. Wait, no, this is supposed to be 1, 2, right? Lambda 1, 2. Yeah. This is the angle between the new one, old, new, old. Angle between the new one, which is here, and the old 2, which is here. New one, old one. I think I need to redo this one because I didn't take into consideration the starting position. New one, old one. New one is here. Old one is here. What is it defined as? Lambda cos theta ij. Does that mean I2j? I assume it does. I2J. So one, new one to old one, new one to old one. Okay, I'll see in the solution what they count as negative and positive. Ah, okay. Angle between new one. This is new one. Old two. This is old two. So this thing, yeah. So that is 90 minus theta. Cos 90 minus theta. Angle between new two. This is new two. And old one. This is old one. Yeah, old one. That is 90 plus theta. Cos 90 plus theta. Angle between old two and new two. This is old two, this is new two. The angle is theta. Cos theta. Okay. We know that angle between new one and old one is cos theta. Yeah. Angle between new one and old two is sine theta. I think that's an identity. Cos 90 minus theta is sine theta. I have a book, an IRL book. I can go get it. I have an IRL book from 1, 2, 3, 4, 5, like 10th grade, 8th. I don't know. I don't know the grades, but I have some trig identities in there. Sine cos theta sine theta equal, yeah. I guess I'll write this down. Where am I writing this down? Might as well write it down right here. Sine theta equal cos 90 minus theta. And the opposite is also true. Cos sine. It's 6 p.m. in Australia right now. Where are you if it's 2 a.m.? Uh, I used to like not really say my location that much, but I'm fine with it nowadays. I'm from the Caribbean. So yeah. It's 2 a.m. Well, now it's 3 in the Caribbean. Okay. Lambda 1 3. Angle between new one and old 3. New one is over here. Old 3 is coming out of the page. So boing, that's like the angle is 90 degrees and cos 90 is 0. Therefore lambda theta. Oh, I didn't expect this 1 to be here. Okay. Lambda theta equal cos theta sine minus sine cos theta. Cos theta sine minus sine cos theta. Minus sine. Minus sine theta equal cos 90 plus theta. 90 minus theta. that is this angle here. 90 plus theta, that is this angle here. Sine theta minus sin. Hmm. Hmm. Cos 90 plus theta. I guess I'll do the maths. Okay. Uh, okay, cos 90 plus theta. Cos 90 plus theta. Cos A plus B is cos A cos B minus sin A sin B. So cos 90 cos theta um, minus sine 90 sine theta. I know cos 0 is 1, sine 0 is 0, sine 90 is 1, so this guy is 1 over here. 1. Cos 90, cos 0 is 1, cos 90 is 0, so this guy is 0. So yeah, cos 90 plus theta is minus sine theta. Yeah, I agree. Okay. Therefore, this is the rotation matrix describing the coordinate changes under a rotation. Under a rotation. So it's general. Uh, Theta under a rotation in anti-clockwise. Anti-clockwise. What if it was clockwise though? If it was clockwise, then I feel like the minus will be up here. I'll have to think about that later. Um, that's so fair about not saying where your located is. I need to twitch. I don't even think about it not being saved. Yeah. Um. Hmm. I have mixed feelings. I have mixed feelings. It's not like random people will be like, "Oh, I'm coming to get you. I will come to get you." But I don't know. It's not that dangerous, but I don't really say much about myself anyways in the first place. Um. So yeah. And Australia is like a big place, so it's not like if they're searching for you, if they're gonna harass you or something, they're gonna have to like find you like exactly. I don't know. I said Caribbean, not where in the Caribbean. Um, Matrices. It is it is worthwhile to review the algebra of matrices at this point. A rectangular array of numbers called elements or matrix elements, Aij, containing m rows. Rows is this, m rows, n columns. Let me draw the lines because this isn't say enough. Rows, columns is called an m times n matrix if it satisfies the matrix operations over here. The definition of a zero m by n matrix also implies the existence of a negative matrix. Okay, Uh, okay, A equal this big thing here, and it's also equal this. A equal, okay, this big thing is called A. Aij. Maybe Aij needs to be inside a bracket. Because to me this just looks like an element, like a specific element. But maybe because I and J are indices, this means that this is actually a matrix in disguise. I'm not sure. A rectangular array of numbers, Aij. Thus m times n matrices are closed under addition, meaning that the result of an addition is also a matrix. Let me look at this. Yeah, being big is definitely for the best. Yeah. How do you say your name right away? Crochet, croquet, croquette, crochet. I assume rye is rye, not ray. Rye, crochet, crochet, croquet, blah blah blah. Equality. C equal A. If matrix C equal matrix A, then Cij equal Aij. Okay. And both A and C are m times n. Addition. If matrix C is equal to matrix A plus matrix B, that means Cij equal Aij plus Bij equal where A, B, and C are m times n matrices. Matrix A is a zero matrix. A equals 0 matrix. The elements of Aij is equal to 0. And A is m times n. Multiplication by a scalar. This C matrix equal alpha A matrix. The elements in C align with alpha, but multiplied by it is aligned with A multiplied by alpha. A is m times n, C is m times n. Matrix multiplication. C equal AB and cannot be BA. A is a m times n, B is a n times L, and C is a m times L. Rows times columns. So in order for matrix multiplication, A needs to have the same amount of columns as B has rows. Okay. A, B, and then the output would be, we don't care about the rows and columns of A, of B and A respectively. We care about the opposite now. C is M times L, which is the rows of A and the columns of B. Rows of A and the columns of B. Boom, 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 boom. Boom, 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 boom. C and rows of M. 1, 2, 3, 4. Rows of M. rows of A, I mean, and columns of B. Boom, 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 boom. Is that correct? M times N. A is M times N. 4 times 4. B is 1, 2, 3, 4. 4 times 5. So now C is 4 times 5. Yeah, yeah. Haha, I couldn't think of a creative username. Say is my name. I couldn't think of a creative username. Say it's my nickname, Ray, and crochet, like the textile craft. Yeah, I was thinking about that. You do with yarn, cause I like to do that. It's still good. It's still good. Pretty unoriginal, but yeah, it's good. It's a good name. Ricochet. It's kind of like Ricochet as well. Ricochet. If you say it fast enough. Ricochet. Okay. It's worthwhile to review a rectangular array contain M and N, blah 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 blah. The definition of a 0 M times N matrix also implies that the existence of a negative matrix. Does it though? Does it though? If you have a 0 matrix, and earlier we established that we use matrices to convert like as a time machine to move uh, functions back and forward in time. 0 matrix. Why have a 0 matrix if there's no way to get to a 0 matrix? Hmm. Is that the logic they're using? I agree with the logic, but I agree with the fact that there's negative matrices, but is that logic good enough? Hmm. At the end of the day, we're just making up all of this anyways. Okay. Thus, M times N matrices are closed under addition, meaning that the result of an addition is also a matrix. Table 2.2 shows the operations that can be performed on matrices. A matrix that remains unchanged under one of these operations is given a special name. For an operation involving a transposition, under which rows become columns, only square matrices with M equal N can be invariant under the operation. A square matrix is symmetric if AJI equal AIJ. It is antisymmetric if AJI equal negative AIJ. The number of rows or columns of a square matrix is called its order or degree. A square matrix, number of rows or columns. Okay. A square matrix in which only diagonal elements are non-zero is a diagonal matrix. A diagonal matrix with ones along the diagonal is the identity or unit matrix I. Its matrix elements are Ij equal Kronecker delta Ij, which makes sense because 1 1 is 1, 1 0 is 0, 0 0 is, well, there's no 0 0 because we start at 1. Okay, I forgot to like look at this, so I'll look at this some more. Cij, so in matrix multiplication, Cij equals, so to get one element, you need to sum up the product of two elements, and the amount you're adding is n. What is n? K equal 1 to n. Oh, and n is over here. N is the number of rows column, the number of columns. So to get one element in Cij, in C, you have to add up n things from the product of the elements of A and B, and those elements are specific. IKKJ. IKKJ. Okay, so we want to find out for C32. We want to find out for C32, which is row 3, column 2. 1, 2, 3. This guy here. To find that out, we need to sum from K equal 1 to, we need to look at A and B. A has 4 columns, so it's 1 to 4. And then we need to look at the elements. AIK. What's I? I is 3. 3K. BKJ. BKJ is 2. 3KK2. So row 3K. Row 3. 1, 2, 3. So this row here. And K2. Row column. This column here. We're summing up A31, B12 plus A32, B22 plus A33, B32 plus A34, B42. Okay, let me get another color. A31, B12, 31, B12, blung, 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 blung. Add up all those to get just one number. So it's really complicated. Okay. The square matrix A to the minus 1 that satisfies the properties the product of A minus 1 and A equal A minus 1 equal I is called the inverse of the square matrix A. A square matrix A that does not have an inverse is a singular matrix. A square matrix A that does not have an inverse is a singular matrix. The sum of the diagonal matrix elements of a square matrix is called its trace. Sum of the diagonal elements, okay. So the trace of matrix A is the sum of AII, yeah. where n is the rank, right? Let me write that. N equal rank slash order. An orthogonal matrix is one whose transpose is its inverse. Thus, okay, for an inverse, inverse is the same as Kronecker delta. Well, Ij, right? Delta Ij. Ij. So this is just dealing with one element. So one element. Okay. I'll write it to the side. 0 if I is not equal to j. 1 if I equal to j. Yeah. Ij, I think so. 1 along the diagonal. Yeah. So OTO, an orthogonal matrix is one whose transpose is its inverse. An inverse is where this is weird. This is weird. Okay. Well, it's a bunch of jumps is all. Like a bunch of jumps in logic all over the place. One whose transpose is its inverse. If the transpose is the inverse, then OT times O. Yeah. Well, I just need to think of this as I. And this is also I. And the reason we have these two equations is to just show that it has the same properties as the inverse. OTO, OOT, I. Yeah. That is the sum of, oh my god, the sum that is the sum of k, OKI, OKJ. Alright, let me draw this. Let's say I is 2 and j is 3. I is 2 and j is 3. Summation over k means we're dealing with inverses, so this has to be a square matrix. So let me change that. Square matrix. O 2 3. So 1 2 1 3. OKI OKJ. 1 2 1 3. Row 1, column 2, column 3. This is weird. OIK, OJK, OIK. This is weird. Let me go back here. For a transpose, AJI equal AIJ. O OKJ OKI Uh, 1, 2, 1, 3. 1, 2, 1, 3. Let me also write the numbers over here. 1, 1. I is 2. J is 3. 2, 1, 3, 1. So column 1, row 2, row 3. This times this plus this times this. So we summon up the product of this. We're summing up the product of this. And that should be equal for some reason. Okay, I, okay, J. Why is that equal? I guess that's the property of a orthogonal matrix. Transpose is the inverse. I guess what I want to see is how an inverse looks like, and that'll maybe make stuff more clear. Okay. These are called orthogonality relations. A unitary matrix is one whose Hermitian conjugate or adjoint is its inverse. Thus, oh my god. Okay. I think this is why I stopped reading like a while ago. Because Hermitians was being weird. Okay, transposition. C equal AT. If C is A transposed, then Cij is AJI, I agree. And A is M times N, C is N times M. If they're both equal, and in this case they need to be square because that's the only way M times N is N times M after changing, after transposing. They are called symmetric. So if you transpose it, and they're equal, it's symmetric. Complex conjugation. So these operations. If you do complex conjugation on A, so it's like A star, Cij equal Aij star. Okay, A is M times N, C is M times N. The matrix is called real, A is called real, if C equal A. Okay. I star equal I minus 1, I equal root 1. I know what I is. I star equal I star equal negative I. What does that mean? Like, if there was a dot dot here, I would be like, oh, they're setting I to minus 1 to minus I. Okay. They're not really saying it here, but what I take this as is they're just changing the sign in front of the I. So if A is this, if A equal Aij equal B plus I assume Aij conjugate equal B minus I. Hermitian conjugation. C equal A Hermitian equal A transpose conjugate. C is AJI, we transpose in and we conjugate in. AJI and conjugate. M times N, N times M. If C equal A, it is Hermitian, or adjoint is just another word. So it needs to be both symmetric and real. Hermitian means symmetric and real. Is that correct to say? Is that a correct conclusion? If C equal A, that means transposing it and applying conjugates didn't do anything. It's for sure square, because that's the only way m times n is n times m. It's for sure square. It's for sure square. Conjugate ai, a plus I, a minus I, conjugate that, and flip it. Okay. Before Hermitianizing it, the minus was here, the plus I was there, the minus I was here. And we don't care about everything else. After conjugating, this guy became plus I, this guy became minus I, and now we're transposing it. This guy became minus I again, this guy became plus I again. So these guys are equal, yeah, but I wouldn't say they're symmetric, because did they say symmetric needs to be like, yeah, they had a definition for symmetric. AJI equal AIJ, but that's not the case here. These two are not equal. So it's not necessarily symmetric. Okay. Real. Maybe it's even the opposite, where it's like it is anti-symmetric. This is not equal this. No, not anti-symmetric. Well, it could be. Because watch. Maybe it is no. If it was anti-symmetric, that means the real counterpart would have to change sign as well. But conjugation doesn't affect this guy here. So I don't think it's anti-symmetric. Maybe if we were looking only at maybe if everything inside was complex, like everything inside was imaginary, then we could say it's anti-symmetric, maybe. Yep. Yep. Okay. Hmm. Is it real? If we conjugate it, it remains the same. Does that mean it was real? I don't think so. Does it? I don't think so. It's for sure square. It's not necessarily symmetric. I think for like the same arguments, it's not real as well, because these guys ended up where they were supposed to be like, oh, it didn't change. But there is imaginary guys in there. Like, and alright, maybe not necessarily real as well. So if it's not necessarily symmetric and it's not necessarily real, what is Hermitian? Hermitian conjugation. Okay, this is weird. They're calling it Hermitian if it's equal. That's weird. That is weird. Okay, we'll find it out. We'll find out the truth at some point. These are called orthogonality relations. A unitary matrix is one whose Hermitian, conjugate, or adjoint. Oh my god. A unitary matrix is one whose Hermitian, conjugate, or adjoint is its inverse. Thus, bling. I agree with this, yeah. I'll have to look at this. UKI, UKJ equal blah 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 blah. These are called unitarity relations. Finally, we know that the order of the matrix multiplication is important. For example, if AB is defined as shown in the last entry of table 2.1, M times N times L. If AB is defined as shown in this, the product BA does not even exist unless M equal L for square matrices M equal N equal L. BA is always defined but may not be BA is always defined but may not be equal to AB. Okay, I understand. Example 2.2.2. Um, A equal 1224 is symmetric. Okay, it's symmetric even though the diagonals are really the same. The trace of A is 5. We just add up the things along the diagonal. This is anti-symmetric. It's symmetric except the minus sign, right? This is Hermitian. C is Hermitian because if you transpose it, so this is transpose, and then you conjugate it. Conjugate this thing. Wait. It's Hermitian because CT equal this and C conjugate equal this, which is equal to CT. Okay. If C equal A is Hermitian, C equal A is Hermitian. C equal A transpose conjugate. Transpose conjugate. Okay. So they don't even need to be together to prove that they're Hermitian. You can do them separately, and if they're equal, it's Hermitian. Okay. I'll let me like circle this in like blue. Boom. Okay, I meant to change the opacity, but oh well, we move. Uh, you AC equal AC AC equal I this. Okay, AC this multiplied by this is, oh my god, 1 times 0 is 0 plus 2 times I is 2I. So over here is 2I. Right. Bling bling. Whoop. Row column. Uh, okay. The row of A and the column of B. Row of A, column B. Yeah, so I'm doing it wrong. Row times column. So it's minus 2i. Next up is this guy times this guy. 2 times I plus 4 times 0 is 2i. This guy times this guy. 1 times minus I is minus I. 1 times 1, 2 minus 1, 0. Minus I. But I'm seeing 4 here. This. Okay, boom, 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 boom. Row, column. Row, row, column. Row. Oh my god. Okay. C. No, I need to go up here. C I J C. Okay, I'm taking a screenshot of this. I can just write it. Paste. Where did the bottom guy go? The thing I used to scroll left to right. I'll just write it. C I J equals summation k equal 1 to n a I no a I k b k j right. Okay. C C11 equal a a1k b k1. Yeah. C12 is a1k b k2. C21 equal a2k b k1 C22 a2k b k2. Okay. A1k bk2. A1k row 1 row 1 uh column 1 row 1 column 1 1 times 0 minus 2. Yeah, good. Minus 2 I. Next up, C12 does row 1 column 2 this guy, yeah, equal A1k bk2 row 1 column 2. Boom, boom. 1 1, yeah. Next up, C21 A2k bk1 row 2 column 1 row 2 column 1 2's. Okay, I see the error of my ways. Okay, we move AC equal this while CA equal this, so AC equal not equal this. AC not equal to AC. What? Oh, CA not equal to AC. Okay. One thing to note is, even though I is only on like half of these, you can like factor out I out of everything. Every element in there got infected by the I. I assume as long as there's an I in each column, that'll happen. Or maybe not, but if there's an I in each column, I, 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 is a big matrix. Boom times boom. If a 0 lines up with the I, this I will not get counted. So not necessarily, but you can still factor out the I from the 0. Hmm. Hmm. 2 times, yeah. I think once there's an I in each column, you can factor out the I, no matter what. And if it's 0, that just means 0 times I is 0. Nothing changes. Blah, 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 blah. Ban, timeout, 1. I guess I'll ban. Goodbye. Alright. Okay. The simplest matrices are 2 by 2 matrices, each of which has 4 matrix elements. It is convenient to express them in terms. It is convenient to express them in terms of the 4 linearly independent 2 by 2 Hermitian matrices. 4 linearly independent 2 by 2 Hermitian matrices. Okay, this transpose is the same as this conjugate here. This transpose conjugate here. This transpose conjugate here. This transpose same as the conjugate here. So I agree, all these are Hermitian. Convenient to express them in terms of the 4 linearly independent matrices. You have I, which is the identity. Then you have these bozos. 0, 1, 1, 0, 1, 0, 0, minus. So that A1 row 1 plus A2 row 2 plus A3 row 3 plus BI equal A dot. It is convenient to express them in terms of the 4 plus BI. You're multiplying A1. What is A1? Okay, well, we're gonna see it here. A1 plus A dot this plus BI. BI B1 A dot this. What does dot product mean? Okay, dot product means you multiply the components by each other, the same components by each other. A1 row 1. Row. Oh, strange. B plus A3. 1, 1. Where do we get this from? It is convenient to express them in terms of 4 linearly so that A1. Okay, let's just look at this first. A equal, is this the matrix or what? What is the matrix? A equal A1, B1, was A2, B2, A3, E3. To me, that just reads as a column vector. A1, A2, A3. Row is column vector. Row 1, row 2, row 3. But the thing is, I is 1001. Well, I could also be this. Maybe that's the thing. I is this guy. Maybe. The matrices rho I were used by Pauli to describe the three components of the spin of the electron, and the spin is a vector. They are called Pauli spin matrices. One can verify by direct calculation that they satisfy the relation multiply two that are not the same, and it'll disappear. I equal j. I equal j means it survives. Okay, so I equal j means it survives. I not equal j means this goes to 0. So we want these to be the same, I guess. If these are different, it's 0. If these are the same, we get the identity. Yeah, these are the same, we get the identity. So what you're saying is if I square this, I should get the identity. 0 times I, 0 times I times 0. Bling bling. 0 minus 1 minus I squared. I squared is minus 1 minus minus 1 is 1. Okay, yeah. The second multiplication is this and this. You get zeros, yeah, zeros. And this guy will end up being this guy is this times this, which is I. It's just minus I squared again, which is 1. So yeah, I guess if you square these guys, you'll end up with the identity. Right? What about this guy? Yeah, yeah. Let me write that. Square them to end up here. Squared. 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 Okay. Oh, but there's also this. Okay. I should really finish reading before I do stuff. So, if they're the same, if they're different, this disappears. But then, you get this term here, which is imaginary, yeah. You get imaginary component epsilon I j k 1, 2, 3. Okay. 1, 2. 1, 2, 1, 1, 2, 2, 1, 2, 3. So if you multiply two different guys, this guy disappears. and you end up with I and the third guy. So can I write that down? Diff results in I multiplied by row k. Yeah, yeah. Orange. Same equal, well, results in I. And I think this should disappear because if I and j is the same, that means the Libesivita will be equal to 0. So yeah, this suggests equal the identity. Identity. Okay. The matrices bling were used by Pauli to describe the true components of the spin of the electron. They are called Pauli spin matrices. One can verify by direct calculation that they satisfy this, where epsilon ijk, the permutation symbol, is equivalent to the relations. I literally just wrote this down here. Yeah. Where ijk is a cyclic permutation of 1 to 3, it is also useful to think of plus or minus I, plus or minus row 1, row 2, row 3 as 8 of the square roots of the 2 by 2 matrix I. 8 square roots. Okay. Unlike simple numbers, these matrices do not commute and are said to make up a non-commuting algebra. I know commutative law is A plus B equal B plus A. Commutative. So not commute. Unlike simple numbers, these matrices do not commute. One plus blend 0, 1, 0, 2, plus or minus. Let me finish reading. The expression 2.13, which is this, of 2 by 2 matrices in terms of Pauli matrices may appear very complicated, but is actually no worse than the representation of vectors by their components. Vector components are extracted from a given vector by taking scalar products. Scalar products. The components AI and B in the equation can be calculated from a given matrix A by taking traces. This is done by first noting that the trace of I is 2. The trace of any of these guys is 0. Yeah. As a consequence, trace of A can be calculated from a given matrix A by taking traces. So let me say A is 2, 4, 5, 3. Trace of A equal AI trace this, A2 trace this, A3 blah blah, B trace 1. Well, what is AI? Well, A1. I think A is also a vector somehow. A1, A2, A3, maybe a secret 0 here. Or maybe one of these guys is 0. The trace of A equal this. A1 times trace playing A2 tracing A3 plus B trace I equal to B. A1. How do we get this equation? Trace of A. Okay, there's 4 terms there, right? So that implies there's a 4 by 4 matrix. Yeah, but the components A, I, and B can be calculated from a given matrix A by taking traces. But we're talking about 2 by 2 matrices. We move. We move. Trace of these guys is 0. So 0, 0, 0, right? Plus 2. Yeah. All these guys is 0. So the trace of A is 2B. Trace of A, trace of the product of A and row 1. Row 1 is, oh my god. Where do we get these from? Trace of A row 1 equal trace of A1I plus A2O. Um, uh, I feel like I missed something. Although I don't think I missed anything. Trace of this equal trace of this equal trace of this. Nothing changed here. We changed these guys from over here. Change these guys from over here. BU01. A1. A1 trace 1. A1 trace of I. A2I. A1. Trace of this was trace of this is trace of this. Trace of what I'm seeing here is the trace is distributed around everything. So we end up with 4 traces. And these guys is 0 because trace of this is 0. So we end up with trace I. A1 is a constant. Is A1 a constant? Yeah. 2AI. Hence A equal these. Oh my god. A, well, the goal is to rewrite a 2 by 2 in terms of these guys. So that should be here. A equal the 3 guys plus identity. This is weird. Row I half trace. Row I half A equal row I half trace. It's almost time I end stream. I kind of want to figure this out. Okay. I might as well change the confusion meter. We go to yellow. Okay. Let me reread all the words to see if I miss anything. The simplest matrices are 2 by 2 matrices, each of which has 4 matrix elements. Yeah, it is convenient to express them in terms of these guys. All of these guys are Hermitian. So that AI, A2, A3. What is AI, A2, A3? What is B? Where A equal A1, E1 plus A2, E2 plus A3, E3. The row vector row 1, E1, row 2, E2, row 3, E3. The matrices row 1 is blah, 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 blah. It is also useful to think of plus or minus I, plus or minus this, plus or minus this, plus or minus as the 8 square roots of, I'm fine with this, yeah. Unlike simple numbers, these matrices do not commute and are said to make up a non-commuting algebra. Square roots. Like these guys or like these guys? Because I feel like these guys commute, right? This plus this equal this plus, yeah. Hmm. The expression 2.13 of 2 by 2 matrices in terms of Pauli matrices may apply variable no worse than the representation of vectors by their components. Vector components are extracted from a given vector by taking scalar products. Scalar product is another word for dot product, right? I think so. You can get the components of a vector by taking the dot product. The components AI and B, any going to one tree, can be calculated from a given matrix A by taking traces. The components AI and B. Trace of I is 2. Trace of these guys is 0. Components AI and B. So we're finding the components. Our goal is to try to find the components. Yeah. Yeah, I think I think the entire goal is to find these guys. We're not given these guys. Okay, that maybe everything changes now that I see that. The goal is to find those guys. Okay. So A, this is our matrix A. Go trace of A. Trace of A is A11 plus A22. A11 plus A22. Trace of A equal so supposedly the trace of A should be the trace of all these guys, the combination of these guys. Does that make sense? I think that makes sense. Because a combination is like, we want to express A, we want to express this, as the sum of these guys, a particular sum of these guys. So at the end of the day, A11 is this times B, no, this times A3, this times A1, this times A2, and this times B. At the end of the day, A11 is these guys added up. So at the end of the day, these guys added up is the same as these guys added up multiplied by the like coefficients. And since the traces of these guys is 0, that means this is 2b, yeah. So I agree with this. Trace of A is 2b, correct. A11 plus A22 is 2b. Hello, is this for quantum mechanics? I assume that's quantum mechanics. This is just like a textbook for like introductory mathematical physics, so technically, maybe, eventually, this is just beginner stuff, apparently. So yeah, I know, yes, I know. Like, yes, you're supposed to know this. Oh, and I guess they are talking about quantum mechanics, yeah. So I guess, yes. Yes, yes, yes. Um, trace of A, trace of A row 1. Why are we doing this now? Row 1. Row 1 is this guy. I have really written up on this a lot. Row 1 is this guy. A multiplied by this guy would be what? Uh, this times this would be, oh my god, A comes first, right? So row times column. This times this is 0, this times this is 1, 2. So A1, 2, the second element should be this times this, no, this times this, A1, 1, this times this, A2, A2, 2, this times this, A2, 1. So we basically just mirrored it. This came here, this came here. And the trace of this thing, the trace of this new guy is A1, 2, A2, 1. The trace of this new guy row 1, row 1, row 1, row, hmm, hmm, hmm. Okay. I was trying to think if there's a shortcut. I don't think there is a shortcut because this is a matrix here. I thought I could like pull it out like a scalar, but no. This is still a matrix. Like a collected book, like ARFCAN or something specialized. I'm not familiar now. What are you studying? Your degree, I mean. Um, degree is like astrophysics. Ooh, spooky. Um, I haven't started. I haven't went into university yet. Like I haven't started the degree yet. I'm just like reading the textbook. Um, like a collected book. Hmm. The topic of the book is mathematical physics. They go into like a bunch of stuff. Bookmark. There's vector fields, vectors and fields in space, transformation matrices and operators, relativistic square root spaces, Fourier series and Fourier transforms, differential equations in physics, maybe nonlinear systems, special functions. I suppose I don't have the title of the book on stream, yeah? I should probably add that. Like, this is the book. Mathematical Physics, CHUN WA WONG. Yeah, I should probably add that to stream. For real. I'm gonna end soon. Uh, hmm, a lot of scrolling. Okay. I'm still not done. Okay. A row 1. A row 1. We saw that A row 1 resulted in this. We're trying to find a trace of this. The logic we used here is, at the end of the day, this diagonal is all these diagonals added up. What about this trace? Hmm. Trace of this guy. The trace of A. We were allowed to do this for the trace of A because we know the end goal is to get these coefficients to be on these matrices. But why are we finding the trace of A row 1? Trace of A row 1 equal trace A1 I A1 A1 row 1 A2 minus I row 3 blah. B trace 1 A3 trace blank. Vom trace. Did this become this somehow? No, I don't think so. I don't think so. Okay, I need to figure out what's going on here. I'll write it to the side over here. A1 2 A1 1 A2 2 A2 1. The trace of this is just A1 1 A1 2 plus A2 1, which is this guy here. This guy. At the end of the day, this guy is these is a trace of like these added up. Transposing. If we transpose this, yeah, I want to make this the new trace. So maybe we don't need to find the trace. We can just see it with our eyes because these are simple numbers. But they have them in terms of traces here. I think I know what's going on. I think I know what's going on. Yeah, I know what's going on. Let me clear this up. This guy, this 0110, is a rotation matrix, I believe. So this rotated the A matrix. So if we apply this to these guys here, they will also rotate. And then if we find the trace of the rotated stuff, we will find the trace of this rotated. So the trace of A01 is the trace of A1. Let me write out what I think it is. The trace of A01 equal the trace of row 1. Well, we need to put in our guys A1, A2, A3, B. Trace of A1, row 1, row 1, plus trace of A2, row 2, row 2. No, row 2, row 1, plus trace of A3, row 3, row 1, plus trace of B, I, row 1. Let's see if this correlates with what we have here. Okay. A1I, B row 1. Trace of I is 2. Trace A1I. Trace A2 row 2 row 1. A2 row 2 row 1. A3 row 1. So I have these guys. I got these guys over here. Let me change color. I got these two guys. A1I. 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 I have BI row 1. B row 1. Okay, I know I can simplify this. Row 1, row 1. If two guys are the same, you can replace them with I. So that's why this guy is I. A1I. So yeah, I have this guy as well. So B row 1. B row 1. I have BI row 1. Maybe I times row 1 will just be row 1. I assume it will be because this is the identity. I times row 1. The I is identity matrix is 1, 0, 0, 1. And what do we multiply by? Row 1. Row 1 is 0, 1, 1, 0. Okay, I'm surprised I figured this out. Okay, this times this is 0. This times this is 0. 0. This times this is 1, 0, 1. This times this 0, 0, 1, 1. This times this is 0, 1, 0, 1, 0, 0. Okay. So yeah, this is row 1. I'm really surprised I figured this out. So good, good. A1 trace I equal to A1 trace I. Okay, minus I row 3. Oh my god. A1 trace I. Yeah. How did these guys tend to 0? I forget. I minus. Where's the eraser? Okay. Row 2, row 1 becomes I, row K. Yeah. Where did the negative come from? Oh my god. A2. Where did the negative come from? Row 2? Oh, I think I know. Because this is Leva Civita. So 2, 1 is different from 1, 2. And the difference is 1 has a negative sign, 1 does not. So, yeah, I agree with this. I agree with this. I agree with this. But where did they go? Because next line, they are nowhere to be seen. Okay, I think I understand. I keep saying that, but um, the trace of these guys is 0, right here. The trace of them is 0. So 0, 0, 0. This is the only thing that survives. That is 2. 2 times A1. The trace of A row 1 is 2A1. The end. Oh, wait, no. We have this guy. So in conclusion, A equals, if you're rewriting a 2 by 2 matrix A, you can rewrite them as a multiple of the identity plus, oh my god, multiple of the identity plus multiples of the row matrices, or the spinor matrices. Pauli spin matrices. Okay. Where did I get the word spinor from? I know I didn't make it up. Did I make it up? Uh, I swear I didn't make it up. It's somewhere. Okay. You can rewrite a 2 by 2 matrix A as these guys. The coefficient of the identity would be, oh my god, trace of air. Oh my goodness. Why couldn't I have just ended stream? I forgot to consider some stuff. Okay. A11. A11. Hmm. The components can be calculated from a given matrix A by taking traces. So we did that. We did that. Trace of this is this. Trace of this would be that. Trace of that would be that. 2A1. Hmm. Half trace this. Row 1. I'll leave it for tomorrow. I'm ending stream. The end. Um, Thank you to these two guys who were here for like a bit. Maybe they're gone. Maybe they're still here. Farewell. Goodbye. The end. The end.